Hello, everyone. Okay, we'll start in a minute. Okay, right. I have changed the board, hopefully for the best. So this is a link to the new board. Now be careful because you can edit it. I will close editing. Actually, you know what? I'll close editing for now. I can view. And so you shouldn't be able to edit now, but there will be a time I will ask you to edit it. So here's a new link. Good. And this, and I've obtained a license for Miro. So hopefully. The reason being that I drew has had problems. Okay, share screen. Lovely. Okay, so let's start. And now in the chat, can you, now the chat is visible to everyone. So do you think you can type something in the chat for me in the Miro board? Can everybody type something? Just say hello in the chat, please, in the Miro. Can you do that? Or the link to the board. So it's here. Here's the link. What? No. So what happens when you try to? You cannot message on Miro. What if I allow you? Can comment. How about now? Still no? What about? I can message on a random place. There's a chat button. There's the chat button on top. So on the top there is, if you press more apps, there's chat. More apps, chat. Okay, I can see comments. I can see comments, but what about the chat? Still no? I can't message, add comments around the thing. Okay. Right. Oh, well, okay. Let's leave the chat as it is for now. I will read out the questions in the chat. We'll see if we can fix that later on. Okay, so let's have a look. Today is Pulleys Part 2. So I've prepared some questions for you on Pulleys. And the there are, so a pulley provides, well, a pulley can provide a mechanical advantage. Okay. Now, let's have a look. Can we find the tension in each rope? And can we find the force that is needed to lift the mass? So let's label this. Let's label this A. So in A. So what can we do? What can we do? How much force is needed? Well, if this force is F, the tension in this rope, if the tension, if you're pulling on this rope with a force F, so the tension in this rope is F. The tension on this rope is also F because it's the same rope. And the tension in this rope is also F. Okay. Now, does that make sense? Does this make sense? Because it's the same rope, the tension along the rope is always the same. Because we're pulling the rope with a force F, that means the tension in the rope is F. Tension F, tension F. Now, if you look at this, bit, you have downwards force, that's tension 2, T2. And then you have here, you have F and F. That means tension in this rope is equal to 2F. The tension on this rope is 2F, and that means the tension in this rope is also 2F. So if you look at this bit, you have 2F and 2F, and that means, and this is the weight. So the weight is equal to 4F. So F is equal to 25 newtons, because that's 100 newtons. Does that make sense? You don't need the chat for now. On a scale of 0 to 10, do you understand how to find F in the first scenario? Okay. Let me just quickly. Okay. Let's go from the other end. Let's go from the other end. I can see some misunderstandings. I started from the wrong end. Okay. Let's do magenta. So let's take this bit. Let's call it A. Pulley A. There's a downwards force of 100 newtons, so the weight is equal to 100 newtons. Now, upwards, there are two equal forces. Upwards, up and up. So what is each force? Well, each force has to be 50 newtons, right? 50 newtons. So the tension in this rope is 50 newtons. The tension in this rope is 50 newtons. Okay? Because, well, we assume it's stationary, or we assume it's moving with constant velocity. All right, now let's look at this pulley, B. Once again, you have a downwards force of 50 newtons. Yes, because the rope is pulling it down with a force of 50 newtons. And there are two upwards forces. Now, because it's the same rope, these forces have to be equal. So if this is 50, this is 25 and 25. And that means F has to be 25 because it's the same rope. This is 25 newtons. So this rope is 50 newtons. The second rope is 25. Well, this is 25. This is 50. This is 25. This is 25. This is 50 and this is 50. Does that, what is the tension force equal to the weight? Well, it doesn't. The tension force is, the weight is 100. The tension force is 50, 50, 25, 25, 25. What do you mean, Mark? Do you mean why are they balanced? Because we assume that the pulley is moving at constant velocity. Assuming it's a non-reasonable, it's not a non-reasonable assumption. Assuming constant velocity. Okay. Well, because the weight is 100 and the force is 25. So the force that you need to apply here is 25. So the mechanical advantage is 4. So mechanical advantage is 4. And there you can argue in different ways why you have this mechanical advantage. Well, the first reason is that this weight is suspended by 4 ropes. Well, technically, it's attached to 3 ropes here. Here, here, and here. Okay, so it's suspended by 3 ropes, and the tension in these 3 ropes is 50, 25, 25. Okay, does that make sense? Now, for the next one, for question B, it's a single rope. It's a single rope. Single rope. That means same tension. Same tension everywhere. Okay. Now, this is 100 newtons. Count the ropes it is suspended by. It's suspended by 1, 2, 3, 4 ropes. So weight is equal to 4 tensions. Yes, because it's tension, 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 tension. And that means tension, once again, is 25 newtons in this case. And the force is also equal to tension because you're pulling on the rope. So the force is the tension, and the rope is 25 newtons. The mechanical advantage, once again, 4. Mechanical advantage is 4. Mechanical advantage, that means that you, with a force of 25, you can lift 100 Newton force. What does it mean? So with force equals 25 newtons, you can lift 100 newtons. Okay. However, you to lift it lift it by 1 meter, you have to pull the rope 4 meters. You have to move the rope 4 meters down. You win in force, but you lose in speed. It's always like that. And that means that the work done is going to be the same. Now this one, once again, it's the same rope. It's the same rope because 1, 2, 3, 4, the rope is the same. It has to have the same tension everywhere. So tension, 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 tension. And this weight is suspended from 3 ropes. And that means that the weight is equal to 3 tensions. Let's call it C. Let's change color. Yeah, so C. So C, the weight is equal to 3 tensions. Okay. And that means that tension is equal to weight divided by 3, which is 33.3 newtons. Okay, so the tension is 33.3 newtons, and the force is of course equal to tension as well. So the force is equal to 33.3 newtons. Mechanical advantage is 3. Mechanical advantage is 3. Okay. Any questions? Any questions here? Mark, does it make sense to you now? Relatively, yes. Another reason why you have a mechanical advantage, if you look at it, if you take this pulley, for example, let's take this bit. Yeah. And you take the pulley. Now this part of the pulley, I think I've explained this before. This part of the pulley can be considered as the pivot. And you are lifting here. You're lifting with a force F here. And then the weight is attached here. So the weight, which is 100 newtons. And let's call this R, and this is R. So the moment, the clockwise moment, is equal to the weight multiplied by R. And the anti-clockwise moment, around the pivot, yes, you're trying to rotate around the pivot. So this force is pushing clockwise, and this force is pushing anti-clockwise. The anti-clockwise moment is force multiplied by 2R. And because in order for it to be stationary, these moments have to be the same. Principle of moment says that the clockwise moment is equal to the anti-clockwise moment. That means that W times R is equal to F multiplied by 2R. And from here, we have weight is equal to 2F. Once again, if this is 100, then this must be 50 newtons. Okay. That means that F has to be 50 newtons. And that's another explanation why you have a mechanical advantage, because the pulley, the movable pulley, is pretty much a lever. Yeah. Let's put this in a quote. A movable pulley is pretty much a lever. Some smart guy. Okay. I don't know who said that first. Okay. Let's have a look at these systems. So same problem. You find F in terms of L. We also assume that the pulleys are stationary. So the stationary or moving at constant speed. Let's start with B because B is the easiest out of all of them. Okay, so let's start with this one. So the tension in this rope is F. We're going to go in terms of F. And this rope is F. This rope is also F. So along the rope, the tension does not change. That's how ropes work. So this is the F rope. Now looking at this pulley, at the first movable pulley, the green one, you can see that there's a downwards force and two upwards forces. So what is the downwards force? It has to be in terms of F. What is the downwards force in terms of F? Luke, thank you. Yes, that is correct. 2F. Because there's an upwards force F, upwards force F, then the downwards force is 2F. That means that the tension in this rope is 2F. So this rope is the 2F rope. So tension along this rope does not change. Well, it's the same, it's 2F. That's how light ropes work. Heavy ropes is a different story, but light ropes have the same tension all the way through. Now, if you look at this pulley, once again, you have 2F up, and that means that the downwards force is now 4F. Once again, here you have 4F and 4F. So the downwards force must be 8F. So the tension in this rope has to be 8F, and here 8F. So the downwards force is 16F, and this is F and F. This is 16F and 16F. 16F. So the downwards force must be 32F. So that means that the load is 32F. So the force is 1/32 of the load. So the force is 1/32 of the load that you're trying to lift. That means you need a force 32 times less than you were trying to lift it on its own. That means you could if that was you probably can comfortably pull, I don't know, 200 newtons of force. Every one of you probably would be able to pull 200 newtons. That means you would be able to lift a load of 16, what? 200 times 32. 6,600. 6,400. Wow, 640 kilograms. You would be able to lift my first car. using that system. It was a Nissan. Okay. A 1986 Nissan. Now let's go to C. Okay, so C, and as you can see, if you trace the rope, it's the same rope. So that means that if this is F, and this is F, and this is F, this is F, then we have a problem. It looks like the system cannot be stationary. Of course it can't be stationary. That's a ridiculous system. Okay, that's what you get when you download things from the internet without checking first. Because what would happen, here is that, let's look at just this part. You have a downwards force. You have, what are the external forces? There's an external force F. That's the left side of the pulley pulling down, F. And then here you have F and another F. So you have two Fs, F and F. So we have two external forces pulling down. That means that the whole thing will just spin. So that means that this pulley will fall down until it hits the mass, and only then it will be able to lift. But then the distribution of the forces would be completely wrong. Okay, so that's a bad question. Don't consider that. The system will not work. And this might not work either, but let's check. Let's trace the rope. Trace the rope. Looks like it's the same rope all over again. Okay, so it's the same rope. That means everywhere the force is F. 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 Okay, so if you look at the load, this is F and this is F. So load is equal to 2F. Oh, that was easy. Oh no, sorry. That's not true. The load, load is connected to two pulleys. Load is connected to two pulleys, and each force is F. So that means the load is equal to 4F. Yeah, that's it. Now the load is connected to 4 Fs. Eraser. Now, will the system work at all? Let's check if there are any inconsistencies. So for example, this pulley, it has F, F, and F. So 3F. So the force in this part is 3F and 2F. So you have 5F here. And that makes perfect sense because the load is 4F and you're pulling with an F. So that's a total of 5F. That's really good. Okay, so it is consistent, so the system will work. It will lift a load, although I'm not sure why you would need such a complicated system of pulleys. But yeah, it's fine. Okay, so let's get serious. Problem 3. We have a system. We have a table. So this is the table. So there's a pulley. Okay, there's a rope. There's some masses, and this thing slides along the table. Slides along the table. But the acceleration is 0. That means it's slide with constant velocity. Velocity is constant. Okay. So we start by drawing a free body diagram on the platform plus mass. So we can consider the platform and the mass as a single object. Okay. As a single object. Can you please draw? So can everyone who has access to this, can you just make a copy here, for example, and draw a free body diagram? Okay, just somewhere here. Hmm. Where's everyone? Can you draw it here, please? Right next to me. Don't go far away. I think there was a button that allows me to. Hmm. Oh, lovely. Very good. Okay. Yeah, very good. Wherever this is. To use a pen, you press P on the keyboard. If you're using a device, then you just that you choose the more apps and choose a pen. Okay. Ikshita, this is not a free body diagram. Okay. The free body diagram only includes one object. So if you've done it correctly, well done. So this is your free body diagram, right? So don't try to make it too complicated. It's just this bit. So if I was drawing a free body diagram, yes, there's no block, nothing, just this. Oh, it's still the rope is still there. Yeah. Very good. And similarly, can you draw the forces on the other two blocks so you can consider them as a single object as well? So that would be the M1 block, the M2 M2, you can consider them as a whole. Yeah. G. Reaction force, very good. Tension. Oh, Luke. Yes, well done. Yeah. Okay. Excellent. You should hear missing one force. It's a rough table. Yes. And because it is moving, yes, we know that it is very good. Yeah, well done, Luke. That definitely is correct. Yes. So we can write M3 minus T is equal to yeah, but acceleration is 0, so you can say that tension is that force. Well done. So for the first, so here I will continue Luke's system. So this is equal to 0 because acceleration is 0. That means that the tension is equal to M3 plus M4G. And from here, T is mu R. Yes, correct. And I will expand on that. So it's mu multiplied by M1 plus M2G. And you can plug that in to here. And you can solve simultaneous equations. That's why we give you that's why the maths topic is simultaneous equations, so that you can work on that. Exactly. So you have 4 forces acting on the block on the table. There's the gravitational force, there's the tension, there's the reaction force, and there's the friction. Because it is moving, we know that friction is mu r. So tension in here, tension has to equal to mu r because it's moving with a constant speed. That means tension is mu r, and r is equal to m1 plus m2g. So we put that in. From the other equation, we get tension is m3 plus m4 g. And so now we can equate them, and we can write m3 plus m4 g is equal to mu m1 plus m2 g. G cancels, and we have mu is equal to m3 plus m4 divided by m1 plus m2. Interesting. Only in terms of, so mu is equal to, only in terms of mass. So all we need is 0.018 plus 0.5 divided by m1, which is 0.18 plus 2. So 0.68 over 2.18. Doesn't look pretty, but 0.68 divided by 2.18. 0.32. 0.32. It's approximate. So it's approximately 0.32. Okay. I didn't have to draw on phone. Yeah, well, no worries. No worries. Try it. later on. Okay, so let's can I just that's convenient. You can't do that on iDrew. Assuming no friction, find at which angle the system will be in equilibrium. Okay. Can I just make some space? And can you just take any square you like and draw a free body diagram for the, I don't know how many of you are here. Draw a free body diagram on the top block, on the block on the slope. Can you please draw that for this, for the top block? Getting more interactive. Okay. G cos alpha. Very good. Yes. All right, well done. But it's impressive. I mean, this is usually quite complicated, even for year 13s. Like a typical year 13 it will be will struggle to do this correctly. And I'm really impressed. Well done, guys. Okay. Anne says I can't draw. Is it more luck now? Is it better now? Oh, if you can't, it's fine. I mean, don't have to. Nice. Very good. Yes, I don't see any problems. I think you're self-correcting yourself based on the others work. So well done. Yes, you've correctly identified that the mass will move up the ramp. Okay. And let's look at the forces acting. So we have for this mass. So for the first mass, we have mg, and there's tension, and it's going to go down because it will go down because it makes makes sense. So mass acceleration is equal to mg minus t. And for the second mass, we have the reaction force, we have the mg force, which is broken down into components. We have mg sine alpha, we have mg cos alpha, we have the tension force, pulling up, and we have the friction force pulling down. And because it is sliding, we know that the friction force is mu r. And we can write two equations. One equation is perpendicular to the slope direction. And we can say that r has to equal to mg cos alpha. Because otherwise it will fly up or down, which it doesn't. It stays on the ramp. And sorry, I don't understand. Show how to draw or what? To draw on the left, there's a more apps button and you need to find the pen. Ah, you figured it out. Good. So in the direction perpendicular to the slope, you have r equals to mg. It has to be like that. And in the direction along the slope, well, we can take this direction as the positive one. We have mass acceleration is equal to tension minus mu r minus mg sine alpha. And using that r is equal to mg cos alpha, we have ma is equal to t minus mu mg cos alpha minus mg sine alpha. So the first question, assuming no friction. So first, like number one, no friction. We have ma equals mg minus t. Oh, we can use that. So you can substitute t is equal to mg minus ma. So here t is mg minus ma. ma equals mg minus ma minus mu mg cos alpha minus mg sine alpha. And this is 2ma equals mg minus mu mg cos alpha minus mg sine alpha. We can cancel the m's. And we have acceleration is equal to g over 2 minus 1/2 mu g cos alpha minus 1/2 g sine alpha. This is the acceleration of the system. Now, assuming no friction, okay, people are still doing stuff. Sorry, I'll pause sharing for can view. I'll pause the editing function for now. Assuming no friction, acceleration, so mu is 0, and that means acceleration is going to be g on 2 minus g on 2 sine alpha. So acceleration is g onto 1 minus sine alpha. What is the condition for the acceleration to be 0? If 1 minus sine alpha is 0. If 1 minus sine alpha is 0, right? That means sine alpha is 1. And the only possible angle, what is the only possible angle? 90 degrees, yeah. If there's no friction, the only way for the system to be stationary if alpha is 90, and that makes perfect sense. Because otherwise, there's the only way for it to be stationary is this. M and M. Right? So the ramp is 90 degrees. The ramp is also a force multiplier. You can use a smaller force to lift heavier objects. The ramp is also a force multiplier. It provides a mechanical advantage. Now, if you see any diagrams how the pyramids were built, you can see them. They're moving blocks up a ramp. So that is provides a mechanical advantage. Although you do have to move the block further, right? You have to move the block a longer distance in order to lift it a small amount. So yeah, that's interesting. Now, find the angle at which, if the friction is mu, find the friction is, so second scenario, friction is mu. Move up at constant speed. Okay, so to move up at constant speed, then acceleration is 0. Okay, acceleration is 0. And that means g over 2 minus 1/2 mu g cos alpha minus 1/2 g sine alpha equals 0. G cancels, and you have half cancels as well. So 1 minus mu cos alpha minus sine alpha equals 0. And that means that mu is equal to 1 minus sine alpha over cos alpha. This is the condition for the system to move down at constant speed. And oh, it's find the angle. Okay, so we need to find the angle. I don't think we can do it without squaring the whole thing. Let's make our life easier for ourselves. Find the condition. Condition angle. All right. Now, if so, we'll slide at constant speed. constant speed. If mu is greater than 1 minus sine alpha over cos alpha, it will be stationary. Okay, constant speed or stationary. Okay, and the answer for this one doesn't. It will not. It will. There's no such angle. No such angle. It will never slide down. Down. You can only slide up or remain stationary if there's enough friction. And so mu is 1 minus sine alpha over cos alpha. Mu is greater or equal 1 minus sine alpha over cos alpha. Okay, so that's that. Okay, find the acceleration of the system and the person in an elevator lift. In a lift. I know elevators on the side of the Atlantic. Okay, so we have 3 blocks and we need to find the acceleration. Of course, depending on the forces, or depending on the masses, it will move up or down. So let's do a general case. Now, I'm sort of doing three free body diagrams at once. So I just don't want to waste time. So there's M1G and there's T1, tension 1, because there are 2 ropes, there are 2 different tensions. That's it for the mass 1, and we can immediately write mass M1. We can write down the equation. So assuming it is moving down, because why not? Remember, if we don't know which way it is moving, we just guess. Assuming main blocks slide up the slope. Mass M1 is and there's no friction. Yeah, so for simplicity, no friction. Mass M1 is going to be M1A is equal to M1G minus T1. That's it. That's Newton's second law for that mass. Now for this mass, M2, so there's M2G. There's the reaction force, R2. There's the tension, T1. There's the tension, T2. Now we break this down into 2 components. This is M2G cos alpha. This is M2G sine alpha. We do a very similar thing here. So we have M3G cos alpha, M3G sine alpha, R3, and T2. So mass M2, we have M2A, mass 2 times acceleration, because it's accelerating that way, it's the forces that help it to accelerate minus the forces that pull it down. Is T1 minus M2G minus T2. And finally, mass m3. Once again, it's accelerating up the slope. So it's m3a equals mass acceleration is equal to the forces pulling it up, T2, minus forces pulling it down, m3g sine alpha. Sine alpha, of course, here. m2g sine alpha. Okay. Now adding the three equations together. So 1, 2, and 3. So 1 plus 2 plus 3. We get m1a plus m2a plus m3a equals m1g minus t1 plus t1 minus m2g sine alpha minus t2 plus t2 minus m3g sine alpha. T1 cancels. Why m2g sine alpha on the left side? Where is it on the left? I don't see. When we split the components, okay. That is okay. I've kind of been avoiding this question, but thank you for asking. Okay. This angle is alpha. Now, I'll draw this force from here. Okay. And we split this into components. So if this angle is alpha, this angle is going to be 90 degrees. And that means that this angle is 90 minus alpha. Do you agree? If we draw, if we split into components, how do we change color? When you split into components, oh, okay. This angle is 90 minus alpha. But we know because the angle between these is certainly 90 degrees. So this angle is going to be 90 minus 90 minus alpha, which funnily enough is alpha. So what we proved that this angle is equal to this angle. And that means that if this is mg, this is mg, that this is mg cos alpha because it's the adjacent side. And this is mg sine alpha. Sine alpha. How do we know? Well, if we draw this vector here, this is going to be a rectangle. Yeah, it's a rectangle. And this side, this is 90 degrees. This side is opposite. So this is mg sine alpha. And this is mg sine alpha because they are the same thing. Does that answer your question, Parichita? All right. So you just need to very carefully look at the triangles involved, and then you can prove. A shortcut, imagine that you're holding onto a handle, which allows you to move it up or down. It allows you to move it up or down. Up or down. Changing alpha. So if you move it down, alpha decreases, but so does this angle decreases. So you can see that this angle is theta. Because if you have a slope, the question is which angle is theta? If this angle is alpha, is this alpha or is this one alpha? Which angle is equal to this one? And you can answer this by imagining that you're pulling the handle down, that alpha decreases. Which of the two angles decreases, 1 or 2? You can clearly see that angle 2 decreases. Angle 2 also decreases. That means angle 2 is alpha, and angle 1 is 90 minus alpha, because angle 2 increases. Does that make sense to you, to everyone? On a scale of 0 to 10, does this make sense to you? That what I'm talking about? Like if you imagine pulling the handle, that changes the angles. Okay, good, nice. Now coming back to our equation, so let's finish this. T1 cancels, T2 also cancels, and we're left with acceleration m1 plus m2 plus m3 equals m1g minus m2g sine alpha minus m3g sine alpha. So acceleration is m1 minus m2 sine m2 plus m3 sine alpha. Yeah, I'm just rearranging it slightly, divided by m1 plus m2 plus m3. Okay. And you can clearly see that if m1 is greater than m2 plus m3 sine alpha, then slides up the slope. If m1 equals m2 plus m3 sine alpha, then it is stationary or constant speed. And finally, if m1 is less than m2 plus m3 sine alpha, g, of course, g. I've taken g out of the brackets. G is here. and then slides down the slope. This slope. So here, acceleration is positive, acceleration is 0, and here acceleration is negative. Negative acceleration means that doesn't mean that it slows down. In this case, what it means that our initial guess was incorrect. So they're sliding down the slope and pulling M1 up. Okay, and finally, the lift. So a house painter is lifting himself up using a pulley. He's pulling the rope in such a way that the reaction force on the floor has reduced to 400. What would the reaction force normally be for the painter? A house painter is lifting. What was the normally? What would the reaction force be if the painter was standing on something? Just, yeah, 720. So usually the reaction force would be 720 newtons, which is equal to the weight. Yes, so Mark is asking, sorry, I don't understand how the second triangle you drew led to the angle being 90 minus 90 minus alpha. I will explain. So this angle is 90 degrees. 90 degrees. And we know that this is 90 minus alpha. So if we want to find this angle, we need to subtract 90 minus alpha from 90. Okay, so this is 90. 90 minus this angle, we get alpha. We get this. Yes, usually so 20. Okay, so 400 newtons. It kind of makes sense. If you're pulling on the rope, the reaction force is going to be lower, right? Because you're pulling yourself up. And okay, so what we need to do is we need to draw free body diagram, and this is what this is how important this is. You always draw one object. You just draw the painter. Okay, this is the painter, and you draw the forces acting on the painter. You imagine what are the objects the painter interacts with. The painter interacts with the ground. The ground pulls him down, which is, let's call it M capital, and this is small m. So mg, that's the force. Then there's the reaction from the floor, pulling him up with the reaction force. There's the tension in the rope that pulls him up as well. Tension in the rope. Okay. And we know that the painter is accelerating upwards because we know that, right? Because it says, what is the acceleration of the lift? The lift, they're both accelerating up. Acceleration. Okay, so we can write for the painter, mass, let's write it here, mass acceleration of the painter is equal to the forces up minus forces down. Tension plus the reaction force minus mg. Now the lift. the lift has weight, so there's a downwards force, mg, mass of the lift. There is a rope pulling the lift up, so tension force in the rope. And there's the, if you're the lift, what do you feel? You feel that there's a person standing and pushing you down. So there's a downwards force, which is equal to R. Because we are considering only the lift only. The person is pushing on you. The person is pushing you down. So when you draw a free body diagram, you have to imagine that you are that object. You are the lift, so you become the lift. What do you feel? As the lift, I feel that somebody's pulling me on the top from the rope. So someone is pulling me here. Someone is pushing me here. And there's gravity. The gravity is pulling me down. And that's all I know. I am become the lift mover of people. Yes. Is that a quote from Oppenheimer? Okay, so does that make sense, Ikshita? Okay. The force that you're trying to say, m plus m, it's actually included here. The mg becomes part of R. And indeed, if you write down mg from here is equal to T plus R minus ma. So R is a part of mg. Or mg is rather part of R. It depends on how you look at it. So we are not forgetting. We're not it's here. It's still there. But it's not a, we don't consider it as a single object. It's a separate object pushing on us, and we can feel that force. And the lift is moving up. We already know that. So mass acceleration is equal to, the force is up, so tension minus forces down, mg minus r. Okay, now we've done the physics part. All we need is to do some maths. Okay, so what do we do? Well, we'll probably subtract because we want to get rid of t. We don't know t, and we're not really interested in t. We'll subtract the equations and by that we'll eliminate t. Eliminate t. And that means that we'll do 1 minus 2. 1 minus 2. So it's going to be MA minus MA equals T plus R minus capital MG minus T plus MG plus R. So T cancels, and we're left with acceleration. M minus M is equal to 2R minus mg plus mg. So acceleration is 2r minus mg plus mg over m minus m. And now we can substitute. So 2 times 400 minus m, which is minus 720, plus 120. 720 minus 120, and that's 800 minus 720 plus 120, divided by 600. This is 80, so 200 divided by 600, which is 2/3 of a meter per second squared, which is 0.67 meters per second squared. Interesting. So we can find the tension with which the person pulls on the rope. Tension is going to be just out of interest. So it's MA minus plus mg plus r, and that makes it 120. No, so 12 times 2/3 plus 12, 120 plus 400, which is 12 divided by 3, that's 4, 8. It's 528 newtons. That's a lot of force. It's a lot of force for one small painter. Not reasonably small, but yeah. Okay. So it looks like he really, really wanted to get up there. But I mean, yes, you can there. That's how you look at it. And it's very important to try to think of the free body diagrams are a difficult concept because you're always tempted to add the masses, but you need to understand that you're considering separate objects, and you're only allowed to use the forces acting on that object. So the painter separate, the lift separate. Just like if you're sitting in the car, there's a force, the car is pushing you up, but you're pushing down on the car. So if you think of it, here's a car. Not very good at drawing cars. As you can see, there's the car seat. And if you look at the forces acting on the car, then there is the reaction force from the ground, reaction force in the wheels. There's the gravitational force of the car, mg. There's the reaction force. And what else? Oh, there's a friction force. If the car is moving, there's a friction force pushing you forward. Friction. Usually cars have front wheel drive, and there's air resistance. There's some friction here as well. Friction in the wheels. There's friction here. Yeah, confusing. Yeah, because friction pushes you forward. Yes, friction pushes you backwards as well. This is the static friction. And this is the rolling friction. rolling. There are two different types of friction. Static friction that is pushing you forward, rolling friction pushes you back. And then finally there's the driver sitting in the seat. But you are the car, you have become the car. You don't care. What is it? What you feel is somebody pushing you. This is the reaction force from the seat, from the person. And this is from the road. This is reaction force from the road. And this is reaction force from the person. So the person is, if you think I am the car, what do I feel? I feel somebody sitting in my seat. Okay. Like you're in my seat. That's Sheldon Cooper. Right. Lovely. I'll stop here. Hope you found it useful. And I'll see you all next week for some maths. Okay. Thank you. You're welcome.